Good morning, students. I hope you all are well. These days, everybody is worried about COVID 19, but be careful, have patience, and do mathematics regularly. These days, we are doing vector subspaces. Today, we will discuss some more example on this particular part. So, let us continue. As you know that a non-empty subset W of a vector space V over the field F is known as vector subspace of V if and only if A alpha plus B beta belongs to W whenever alpha beta belongs to W and AB belongs to F. In the last video, we have proved this in the form of theorem. This can be used as a definition also, but you remember the basic part of this? A non-empty subset W of a vector space V over the field F is known as vector subspace of V if W satisfies all the axioms of vector space. That means all 10 properties must be satisfied by W. In short, if W is closed with respect to addition as well as scalar multiplication, then W is known as subspace because the remaining 8 properties will be inherited from V. In that, we have to prove the closure property, but this way, if we consider, then this is a single part of this one. So, non-empty subset, this is the second definition, a non-empty subset W of a vector space V over the field F. If the field is not given, we will consider the field is a set of real numbers, is known as vector subspace of V if and only if A alpha plus B beta belongs to W whenever alpha beta be the members of W and A be the scalars of the members of the field. Okay, here this theorem is, we have proved this theorem in the last video. Here it is written if and only if. So both way you can consider this way. So more example I consider. Always remember this particular property. Whenever you have to prove the given set is a subspace. Let the set of n by n matrices of real entries. This is the set of n by n matrices of real entries. This is a vector space under addition and scalar multiplication. Okay, so here it is, the set of n by n matrices of real entries. That means all the entries of this particular one, the real numbers. This is a vector space we have already proved under addition and scalar multiplication. That means component wise addition and scalar multiplication. Let M be the set of 2 by 2 matrices. A belongs to such that A is a symmetric matrix. A is the member of this, but you remember here this one is fixed. I have considered M is a square matrix of order 2 by 2 and A is a member of this one. That means you have to consider all 2 by 2 matrices in such a way that A is a symmetric matrix. Obviously, two by two is a subset of n by n. So here this is the non-empty subset of this one. Now the condition is A is a symmetric matrix. Now you must remember a symmetric matrix is always a square matrix. And definitely we took the matrix of order n by n. So this is a collection of all square matrices. So a matrix is a matrix is a symmetric matrix if its transpose is the matrix itself. That means instead of this one I can write, sometimes this is rewritten as A belongs to the member of this and transpose of A equals to A. So A is a symmetric matrix if transpose of A is A. Okay, so let us prove this. Let A and B be two matrices of order 2 by 2 such that transpose of A equals to A and transpose of B is equal to B. That means A and B belongs to this. Two matrices of order 2 by 2 such that transpose of A is A and transpose of B is B. Now, equals. Where A and B are scalars. So this is this condition must hold. So we begin with this one. So this says this is the property of transpose matrices. If you remember in class 12 or maybe in first year, whatever theory of matrices, if this is a matrix, this is a matrix, then transpose of sum of two matrices is the sum of transpose matrices individually. So it is like this, and this is Okay, again this is the property. Now since A and B are symmetric matrix, so instead of this one and this one, right, this is number 1. So this is AA plus BB using first. So transpose of the whole is equal to this one. So if I say, suppose this is P, so it is transpose of P equals to P. If transpose of P is equal to P, that means P is a symmetric matrix. And if P is a symmetric matrix, then it must be a member of this particular one. Okay, so here it is. Therefore, this implies belongs to, I repeat, A and B be two matrices of order 2 by 2 such that transpose of A equals to A and transpose of B equals to B. That means A and B are two symmetric matrices of order 2 by 2. So they are the members of this particular one. We have to prove this is a subspace of set of matrices of order n by n. So we begin with this. We try to prove transpose of this particular part is equal to the matrix itself. So A is a matrix. If matrix A is multiplied by scalar component wise, then again this is a matrix, this is also a matrix. So transpose of this is equal to this. This is the properties. Then it will be this. Here it is this. So if I say this is P, for example, this is P. So it is transpose of P is equals to P. That means P itself is a symmetric matrix. That means this belongs to M2 by 2 because this set has the collection of those matrices which are symmetric. This implies M2 by 2 is a subspace of n by n with the given condition that transpose of A is A, that means A is a symmetric matrix. Okay. You try yourself. And 2 by 2 A belongs to n by n such that transpose of A is minus A. That means A is a skew symmetric matrix. Now we come to the next question. Look at this. V is R cubed. V is R cubed, that means 3-dimensional space, you people know that. V is R cubed over R and the subsets V1, V2, V3 are defined as follows. V1 set of points in 3D such that x plus y plus z is 1. The condition is given. Just like here the condition is given, that means transpose of A is minus A, so A is symmetric. Second one, again the point is in space in 3D. With this condition x plus 2y plus z is greater than root 2. V3 x, y, z such that x square plus y square plus z square is less than equals to 1. You remember, this is the equation of plane. I am giving you the hint. This is the equation of the plane. This is, if the sign is sign of equality, then it is the equation of plane, but it is upper part of this one. If the sign is here equal, then x square plus y square plus z square equals to 1. That is the equation of the sphere surface. But it is less than and equal to, that means the whole surface and every interior point of this sphere. Okay. Which of these is a subspace of V? This you have to prove. Second question, let V equals to C of 0, 1. This symbol is already explained. In general, I write it is A, B. That means it is closed interval, and this is the set of real valued functions on this given interval. The subsets V1 and V2 are defined by this one. So here what is V? V is a vector space. The set of all real valued functions defined on this particular one, and you people know that the set of real valued functions on the given interval defined on the given interval is a vector space under the addition of functions and the scalar multiplication of the function. This we have done. So this is a vector space. The subsets V1, V2 defined by these two. Here fx means V is a set of functions. So the integration of f of x under the limit 0 to 1, the answer is 0. And here it is 0 to 1, f of x dx equals to 1. So these are two parts you have to prove. Which one is prove or disprove? Which one is the vector subspace of this particular one? One of the parts here be given, so I will give the hint. If you consider the geometry, remember one thing more. We people know that if W is a subspace of V, then W must contain the zero vector or null vector or zero element. Of V. That means the identity element of V is also the identity element of the subspace. So this is the trick. If W is a subspace of V, then W must contain the zero vector or null vector of this. It means if we want to prove the given set is a subspace of the given vector space, the shortcut is you just identify the zero vector is the element of W or not. If it is, then you can proceed. So I am giving the hint. It is x plus y plus z equals to 1. And if you remember, this is already explained. Here it is. This is the origin. You remember, this is 0, 0, 0. So all the points lying on this plane are the members of V1. And what is V? V is the collection of all the points in three-dimensional space. So this is the part of R cubed. This is the part of R cubed. That means this is the subset of this one. So here V1 is given in such a way that x plus y plus z equals to 1. That means all the points lying on this plane. And we people know that this is a subspace, this is a vector space, that is R cubed with the regular operations, that means with regular addition and scalar multiplication, and under that we know that 0, 0, 0 is the identity element. That means this point is the identity element of this V. This is the null vector. Zero element of this one. So if this V1 is a subspace, then it must contain the zero vector, and you say this point is not lying on this one. If we consider 0, 0, 0, then it is not satisfied by this one. That means this does not contain the origin. Hence, this is not a subspace. So looking at this one, immediately you can find the answer. Yes, this is not the subspace. In the similar manner, you can see the answer. You can see V2, it is above than this. Here you can write root 2, then it is greater than root 2. That means it is this side of this particular part. And this I have already explained. So you just try all these questions and mention the answer in the comment box. If you have difficulty, you just comment on it. Okay, so thank you. God bless you.